Once again, good morning to all. This is Dr. N. Ravisankar Reddy, working as Associate Professor in Electrical and Electronics Department. Today, we'll continue the last session. Okay, it's control system subject. Now, we'll discuss the time domains of the second chapter of the in our syllabus, time domain analysis. Right. So, time domain analysis. So, any system contain the energy storing element like inductor, capacitor, and mass and inertia possess the certain energy. Okay, so these energy storing elements are the part of the control system, and it is the energy state of the system is distributed. Then it takes certain time to change from one state to another state. So that the disturbance sometimes occurs in input, sometimes occurs in output, sometimes at the system. Then the time required to change from one state to another due to known as transient state. Then the value of the current or voltage or any parameter in this period is called as a time response. The transient may have oscillations which may be either sustained or decaying in nature. So this will depends upon the parameters of the system. For any system, we can get the by linear difference equation. So the solution of the linear difference equation, the equations gives the response of the system. So the time response of the system, the time response system is the output of the closed loop system as a function of time, and it is divided and it is denoted by C of t. Then the time can be obtained by solving the differential equation and governing the system. Alternatively, the response C of t can be obtained from the transfer function of the input and to the system. So the output in S domain, that is C of S, is given by the product of the transfer function of the input, that is R of S, and on taking the inverse Laplace transform, this product in time response C of t can be obtained. Right. So this is the simple, already you know this is the simple closed loop control system. So this is R of S, then you are taking the forward gain, then feedback gain H of S. So already you know, so you are taking the feedback is a negative feedback here, right? So now the transfer function of the C of S bar of S equal to G of S plus 1 plus G of H of S, right? The response of the in S domain, output in S domain responsibility, you will take the output only C of S. So take the R of S this side, right? So now it is R of S equal to G of S into 1 plus G of H of S. Now taking the, so how to find out the in time domain, supply the inverse Laplace transform. So L of inverse. So the time is control is two. Generally, the time response in two parts. One is the transient response, one is the steady state response, right? So the transient response of this was the response of the system when the input changes from one state to another state. Is the called as a transient response of the system. So these are the then again second of the steady state response, right? Now coming to the transient response, the part of the time response which goes to zero after a large interval of time, transient response. So in this case, that is the limit t tends to t tends to infinity, C of t equal 0. So from transient point of view, we have some small information I am giving here. So the time interval of the after which the system response taking the instant of applications excitation as the response reference, then the total time that it takes to achieve the output for the first time, then whether the output suits the beyond the desired value or how much of the value, then whether or not the output oscillates about the final value, then the time that it takes this to settle the final value. So this they call as a transient response. These are the few points. Then coming to the steady state response, so the part of the response remains even after transients have died out. That's said to be steady state response. So for steady state response, we get the following some information, that is some points. The time that output takes to reach the steady state value, whether or not any error exists between the desired and the actual value, whether this error is constant or zero or infinite. So now I am representing the time response with the two functions. One is the transient response, one is the steady state response, right? So this is the response of the system. So the first part you can observe here. So this is the first part, is called as transient response. Okay, so you can see the response is varying with the time. You can observe here the response is varying with every instant of time. The response is varying, right? Now you can, after reaching the some value, call it steady state value. So actually I want the output at 1, but it reaches 0.9 output. So this is called as error. The small difference between the our expected output and what you get the output from the response, call it a small error, right? So this is called as a transient response. Then the other meaning called is steady state response. So this is the simple representation of the steady state and transient estimate of the any system, right? Then coming to the our control system transfer functions, you give any transfer function. So this represented in some polynomials, right? Some polynomials. So this is the one of the polynomial to represent any transfer function, right? So here in this case, the transient response generally it depends upon the nature of the denominator polynomial. That is very important. Denominator polynomial. So the nature of the output and error that depends on the denominator polynomial. What is denominator in our control system? In a standard closed loop transfer function, so this is the denominator 1 plus g of h of s. 1 plus g of h is the polynomial. So this is very important. It's called as characteristic equation, right? So this is the denominator polynomial will give the information of the transient response error and output, right? So this is called as characteristic equation I mentioned here, right? So the roots of characteristic equation called as a poles. The roots of the characteristic called as a poles, right? The poles of the transfer function. The poles is called as a closed loop poles, right? Closed loop poles, right? So here the poles of transfer function are the values of s at which the function becomes infinite. That is very important, right? Then the zeros of the transfer function are the values of s at which the function becomes 0. And the Laplace transform variables s represent the complex frequency, that is s equal to sigma plus j omega collisions. This is called as real value or imaginary value, right? So alpha called as a Nepper frequency, and omega is called as a radiance frequency. Generally, already we are representing in different forms. Okay, a plus j form. So imaginary, this real part, imaginary part, right? Or angular, or in polar forms, you can represent magnitude and angle. Then represent the polar form. So there are different methods to represent the values. Okay, so in this case it's called a real value and imaginary value. So in this case we call as a sigma is called as a Nepper frequency and omega is called as a radiant frequency. Then so in general the transfer function we are represented in polynomial. So C of s by R of s, right? So these are a m s power m, a m minus s power minus 1, like that we will go up to a0. Similarly the denominator also bn s power n, bn minus 1, s power n minus 1, so like that we'll get. So in this case the denominator will represent the poles, the numerator represents the zeros. So this is the general format in the control system represent with the system, that is called a transfer function, right? So this is called poles, these are zeros. Okay, so it's one of the important representation of the control system transfer function in control system, right? Then again to the other topic is the type and order of system. So this is very important in control system. Type and order of the system. For a given system, you have to see what is type, what is order. Right? Let us see what is type, what is system, how to find the type and order of system. Right? So consider the transfer function here already given. So 1 plus s to 1 t1 s 1 plus t2 s, then s power j 1 plus tas 1 plus tbs. Right? So here j is the type of the system. That is, suppose you take the one system, an example k by s into s plus 1, right? So here the power of the s, so this is the type of the system. Suppose some transfer function there is no s, suppose this is s plus 2. Okay, though here s is not there, so this is a type 0. Now is s power 1 is there, so this is type 1 system. Clear? Then how to find out the order means, if you observe this, if you multiply with this one, what will happen here? S square plus s. So what is the highest order here? S square. So this is second order. So in this case is the first order. Okay, suppose I take s by s square plus some s plus k. So these are type. Okay, so that multiplication, when we multiply all the terms in s, that's called highest order. Call it highest order. Okay, suppose I take s into s plus 1 into s plus 2. Now how much we multiply all the things, how much highest order of the s into s, so how many s are there? 3s. So order is the 3. Okay, now I suppose I take s square. right? Now what is the type, what is the order of the system? So here the type means s square is there, so 2, so type 2. What is the order now? S square, one term s square is there, again s is there, one s is there, so s cubed and s power, so the fourth, that is okay. So that is the second type and order is 4, type 2 order is 4, so like that you have to find. So the very important, the type and the order of the given transfer function. So this is the way to give the type and order. So how to recognize the type and order? This is the way, this is a simple method, right? So the s power something, some power 0 or s power 1, s power 2, so it gives the type of the system. When you observe in denominator, how many s's are there? How many s's? 1, 2, this one, order 2. Coming to here, see, s power 2, s. So here you will s power 3 and s. So these are type 2 and order 4. So like that we have to find the type and order of the system of a given transfer function, right? Now coming to, so already I know this is the transfer function, closed loop transfer function, classic equation 1 plus g of s is classic equation, right? The highest power of s represents classic equation called as a order of system. I already mentioned, you can observe here, the highest power of the s present in the classic equation system is called as a order of the system, right? Then, so there are different types of inputs used in a time domain analysis. So inputs here, what is excitation or input? So R of s, right? So generally what is transfer function? C of s by R of s. So C of s is the output, R of s is the input, that is called, you call as excitation, right? So here there are different types of signals you are using in a control system, right? So these signals are standard signals, right? So this is the step signal, ramp signal, periodic signal and impulse signal, right? Suppose the value of step signal 1, they call it step input, okay? So therefore the value of the ramp is the 1, so this is called unit ramp. If the value of the one parabolic is 1, is called as a unit step, that is a unit parabolic signal. If the value of the simple signal 1, this is called unit ramp. So these are the type. So these are the signals you are using in SMAS of systems. So in most of systems, input signals may be known as ahead of the time, or also it may be difficult to express the input signal mathematically by simple signals. So the characteristics of the actual input signals are sudden shock or sudden changes in constant, so velocity, constant acceleration, like that. So the such signals are resembles these characteristics and used in input signals of period or performance of the system. So the commonly used input signals, these are the commonly used signals, okay? These are commonly used for a control system, right? The signals of time is maybe classified, generated and elaborated, or mathematical expressions. Okay, we can represent with mathematical expressions of each value, right? And take the first signal, so they call it step signal, right? Step signal. The step signal is a signal whose value is from 0 to a at t equals 0. That is, when t equals 0, the value is some value. Okay, it may be 10 or 20 or 30, it may be. So remains constant for a t greater than 0. And is remaining constant as time remains constant. The value is constant, but the time is varying. You can observe here. For time is varying, but the value is constant. So just like a DC in our electrical system, if you told this is just like a DC, right? Right, so I represent generally I take the R of t. So R of t A into E of t. So E of t is 1 when t greater than 0 and E of t equals 0 when t is less than 0. Okay, so then find the in edge domain the value of the R of t. So R of t equal to A into E of t. So what is the value of the E of t unit value in a Laplace transform? So take the simple L into E of t, so 0 to infinity E of t into e power st minus dt, right? Laplace transform dependent, already know. So 0 to infinity, so this is a constant value, so it will come 1. So e power st dt, so e power st, so by taking the limits 0 to infinity, after integration you will get e power st and minus s. So substitute limits, lower limit and upper limit, will get the value of 1 by s. Clear? So 1 by s you will get value here, okay? Right? So this is so when you apply this step into E of t, that in time domain the step signal is A into E of t or 10 or 100, whatever it may be, okay? Then so what is the value of the Laplace transform is called 1 by s. Suppose I take 10 E of t. What in Laplace transform it is A is constant second, so it is 10 by of s. So constant same, so 10 by s you will get here. Right? So similarly the input signal, so now the input signal is 1 by s. The input signal is 1 by s, so for step input, right? Then coming to Next signal, ramp signal, right? So ramp signal is the signal whose value increases linearly with the time from initial value to initial value of time 0 t equal 0. The ramp signal resembles the constant velocity input to the signal, so in which the value a is unity. So the mathematical representation of the ramping signal is r of t equal to a into t. Okay, when it is value a into t when t is greater than or equal to 0, when r of t equal to 0 when t is less than 0. So these are representation of the ramp signal, right? So for one value there is some value, for two is a value. So that is with the time you can observe by changing time the magnitude also is changing. In previous case you can observe the step input only the value is constant like in DC, but here the value is changing, but it is proportional, but is varying to the proportion, right? So what is the, now apply the Laplace transform, then find, so 0 to t and infinity. So Laplace is obtained by multiplying the r of t by e into st minus st, right? So now r of t equal to 0 to infinity r of t d power minus st by dt. So what is r of t here? A t. So a and time e power st by dt. So t is there. So in equation when t is there, it equal to 1 by s square. So a by s square. Okay, clear? A by s square. So whatever the value of a maybe, so as it is a constant will come outside. So 1 by s square. So r of s equal to 1 by a s square now. So for a step input, the r of s is 1 by s, the ramp input 1 by s square. So okay, so this is the representation of the ramp input, right? Now coming to the next signal, parabolic signal. So parabolic in mathematics, parabolic, right? So this is the parabolic. So r of t equal to a t square by 2. Okay, t greater than equal to 0. When t less than equal to 0. Okay, so these are, so it is the representation of the parabolic in a graph. So the representation, no, parabolic. Okay, so what is the in time, which is a t square by 2. Okay, now take the Laplace transform. So r of t equal to a t square by 2. Now multiply with e power minus st dt. Now so here t square by 2. So t square means you will get the how much? T will get, so it is t cube, so it comes to the 1. So it is t cube, right? So a by s cube will get. So in a when integration it, you will get the a by s cubed. Okay, a by s cube. Now if you get the t square value, you will get the cube, right? So one value is more, right? So previously you can observe t is game at, what you will get? A by s square. Now t square by 2, so a by s cubed. A by s cubed. If the function a equal to t, so 1 by s cubed. So we call it unit parabolic function, right? So this is the, you can find the in time domain to Laplace transform for each signal, right? So the another one is a impulse signal. So impulse means at very small time the value exists. Very small time, so the value exists. So this is called as impulse. Very small time we get the value, right? So a signal which varies very short duration we call as impulse duration. So ideal impulse signal is the unit impulse signal. So which defined as a signal having 0 values at all time expect to t equal to 0. Okay, so these are representations. So limit t tends to 0 minus t1 by plus t1. So del t dt equal to 1 value. Okay, if you do in differentiation this one, so you will get only one value. Okay, so r of is equal to 1. So for a impulse in the r of is equal to also 1 you will get here because it's constant, right? These are, so this is the response of the impulse signal, right? Now I am giving the small comparison table for examination purpose. When you keep, it is very easy to keep it in mind. Okay, so step input, step means only the constant value a. So in Laplace it is a by s. Unit step input, the value is no, so 1 by s here. Then ramp input, so at, so you'll get the a by s square. So unit time only t, so 1 by s square. So just the constant value will disappear, that's all, right? Next, parabolic, say it is square by 2, so a by s cubed. If it is unit parabolic, t by t, so 1 by s cubed, right? So coming to the impulse, so it is a very small instant value, so it is a constant value. So very easy to remember in a, for exam point of view, this table is very useful, right? Now take the order of the system. Now I am taking the first order. Okay, so already told the first order means, no, already I told in previous slide. So a by s plus a, r1 by s plus means also first order. Okay, right? So this is the first order. There is no type here because there is no s term. Okay, there is no zero type, right? Zero first order. So the how to represent the first order, that is the unity, that is the feedback is unity. The feedback to the input system, here the value is the infinity. That is the gain in a feedback is the value is unity. So when you do it, so generally what is the transfer function of the closed loop transfer function? C of s by R of s equal to G of s by 1 plus G of s into H of s, right? Now H of s is 1. Okay, now take A by s divided by 1 plus A by s, right? Now take the here LCM again, so A by s, so s plus A by s, so s cancel, so we'll get a by s plus a, right? So this is the result, right? So now you have to find the step time. So generally in our syllabus, so you are using only the step input only. You are not using the remaining inputs. What are the remaining inputs? Parabolic. Okay, remaining you are not and ramp input you are not using in our syllabus. Only by applying the step input, what is the response of the system, right? And only you are using step input, right? Now take the partial fraction. So I'm taking a by s into s plus a. So already you are very well this method, partial fraction method, already you studied in mathematics in high school or maybe intern, right? So partial fractions. So how to find out the constants a and b by using partial fractions. Okay. Now you equate the denominator and numerator values, right? So I'm taking the s into s plus a cancel out. So a equal to so the a by s, so s plus term not there here, so multiply s plus term with a. Then coming to b plus s plus a, so s plus term is there, not in the s plus is there, so multiply with b into s. Okay, now compare with the RHS and LHS. Okay, now either the here there is a constant value there, so s term, there is no s term here. Okay, so this is LHS, this is RHS, right? So in LHS side, the only constant term is there is no s term, because you can see here as plus aa plus bs. Okay, so s term is there, s term is no s term here, so it's 0 automatically. So if you want, I can do it here simple, as a plus bs, clear? So compared to LHS, RHS, so s term is 0, there is no s term in LHS. Okay, so s equals, put s equals 0. When you put s equals 0, only term aa will remain. Okay, so aa, so here this is the constant term. Okay, so what is the constant term here? Here coefficient is 1. Okay, the coefficient I have taken 1, so aa equal to a, so aa cancel out, so a equal to 1. Okay, similarly put s equal to s minus a, so what is this? So all taking the s equal to 0, s plus a equal to 0, so s equal to minus a. Now substituting s equal to minus a in our equation, so what will it here? So a into, so b into minus a, so b equal to a cancel out, right? Equal to b equal to minus 1. So like that you have to find the partial fractions. Okay, this simple method to find the a and b value. Now substitute here, so c of s equal to a value 1 by s, b value is minus 1, so minus, so 1 by s plus a. Okay, now apply the inverse Laplace transform. So inverse Laplace transform, 1 by s is 1. Okay, 1 by s plus a e power at. Okay, now the response in time domain is c of t equal to 1. Say I'm substituting here, Okay, 1 minus e power at and t is greater than equal to 0. So this is the response of the first order by applying the step input. This is the response of the first order system by applying the step input. R of is equal to 1 by s, right? So this is the response of the first order system when apply the step input. So the response is like this. So because it is e power, what you got here? E power at. So e power at means we will get like this one, e power at, right? So this is the response of the first order system when apply the step input, right? Then it's coming to the second order of the system. Okay, so second order system is what you will get. I told what when you multiply with the s into s plus, you will get second order system. Second order system, right? So this is the second order system. So k by s into s plus a. Okay, already I told. So this will get k by s plus a. What is same? G of s by 1 plus g of s into h of s. Okay, so e power So g of n into h of s. Substitute same here. So k by s into s plus a divided by 1 plus k by s into s plus a into 1. Now take this plus this side. Okay, automatically this will cancel out. So k by s square plus sa plus k will get. So they will get the same value. Okay, multiply here. Okay. What I would do this here. K by s into s plus a divided by, so come here. So s into s plus a, right, plus k divided by all divided by s into s plus a. So this is cancel out. Okay, now k by, so multiply with the s square plus sa plus k. Okay, so this is also k by some first, right? So like this you got the second order system, right? So these are the response of the second order system. So these are the response of the second order system, right? So this is the transfer period. Again go to the unit value. So we call it unit value. So when above the unit value, then I come to the sun value. So what is the practical example of second order system? Can you know? So I think all electrical students are, maybe ECU students are going to practical. Okay, for practical you can see the meters, either a meter or voltmeter. Are you observed the response of the meter? Meter means that needle. What is needle inside the meter? No, somewhere nowadays you are using digital meters also, but take analog meters. You can observe when it connected to the supply, when a circuit, when it's on the supply, you can observe the needle of that meter. What will happen? Suppose I given the voltage 230 volts. Okay, so if it digital meter, it will show 230 or 231 or 229. But analog, what will happen when the needle will, suppose is the 230 value is there here. Okay, so the needle will, what will happen? The needle will go from 0 to some value or 230 to 235. Again come back, again go back, and then at the end it will stop on somewhere. Okay, so this is the response of the system. So we go beyond the 230. Suppose this is the 230. So beyond the 230 it will go. Again come back below. So below return back again to this one. Again go back. Again. So at some time, after some time it will settle down to some value. Okay. So this is the best example for second order system. So you need to take any analog meter, right? Set ammeter or voltmeter or wattmeter, or it's a meters you are using in our laboratory. So the best example. So that is the second order system, right? Okay. So this is the response of the system, right? So now take the classic equation. So I told the classic equation is the denominator of the second order classic equation, right? So s square plus as plus k equal to 0. So s1, s2. So minus a. So you take the roots of the equation. Already you know very well how to find out the roots of second order system. So minus b plus or minus root of b square minus 4ac divided by 2a. So like you can find out here. Clear? So this is a standard finding the roots of the second order equation. B minus b plus or minus b square minus 4ac by 2a. So from using this equation you can find the roots of this s1, s2. Right? Then analysis of second order system. Now generally you are using second order system in time domain analysis. So second order system is a standard format is using here. Omega n square s square 2 zeta omega n s plus omega. This is the standard format. Okay, this is very standard format using in the control system, right? So every practical system takes a finite time to reach the steady state. So during this period the oscillations are exponential. So the behavioral system gets decided by the type of the closed loop poles and the location of the closed loop in S plane. Okay, the closed loop poles depends upon selection of the parameters system. So every system has tendency to oppose the oscillating behavior of the system. So which is called as a damping. Now the tendency controls the type of control loop poles and hence the nature of the response. So it depends upon the poles, the response of the system is different. Okay. So the damping is measured by factor called as damping ratio. So damping is measured by a factor they call as a damping ratio. They call zeta, right, of the system. So the factor explains that how much the dominant opposition from the system is to be oscillations to the output. So in sometimes it will be low, in which the system will be oscillate, but slowly or with damped frequency. So sometimes it may be high, so the system output will not oscillate at all time, and only that will depends upon the exponential. So slow that will be, so that will takes very long time to reach the steady state. So the damping ratio explains the such that the behavior of the denoted by the symbol zeta. So we call it Greek word, we call it a zeta. Greek word, this is zeta. So it is so if it is 0, the system is called as a, it is the system is maximum frequency, and there is no opposition for the system. Then it is naturally freely oscillations under this such condition. Hence the frequency of the oscillations zeta equal to condition called as a natural frequency oscillation. When zeta equal to call a system, we call it natural frequency oscillation system. Okay, then and it is denoted by the symbol omega n, denoted by the omega n, called as natural frequency oscillations. Right. So for a second order system behavior, the closed loop transfer function quotation. So the coefficients of the equation are directly related to the zeta and omega n. Okay. So the second order system is directly proportional to the zeta and omega n. Okay. So this is the standard equation. Second order system. So the denominator what is appearing here, this is called as a classic equation of the second order system. Okay, classic equation. Okay, so here omega n is the undamped natural frequency, so it is radians per second. Then zeta is the damping ratio. So depending upon the value of the damping, we call the system is different type. So take the case 1. So what is damping ratio? It depends on the ratio of actual damping to the critical damping. Okay, the response of the time C of t is second order system depends upon this the damping ratio. So depends on the value of the zeta, the system is classified in four types. So one is called as undamped. Undamped, when zeta equal to 0, called as undamped. That is underdamped. So zeta between 0 to 1 is called as undamped. Right? When zeta is equal to 0, 1 is called as critically damped. When zeta equal greater than, you call it overdamped. Okay, it is called as overdamped. So there are 4. So depending on the value of the zeta, there are 4 types of the system. So one is the undamped, zeta equal to 0. Then is underdamped between 0 to 1. Then it is zeta equal to 1, you call it critically damped. When zeta is greater than 1, you call it overdamped. Okay. So these are classic equivalent second order system. Already I told how to find out the roots of the any second order system by using mathematical equation minus b plus r minus root of b square minus 4ac by ta. So by using same method, you are finding the roots of the classic equivalent s1, s2. Right? Same equation. So again I am writing minus b plus r minus b square minus 4ac by 2a. This is the standard equation to find the roots of the any second order system. Okay, second order equation, right? So by using same equation, now minus omega zeta n. Okay. Now already what is the equation? A square x square plus bx plus c equal to 0. This is second order. I will write once again neatly. So this is the standard equation, ax square plus bx plus c equal to 0. Okay, ax square bx plus c. Same here, observe here. The coefficient is 1, s square 2 zeta omega n is omega n square. Okay, s square s term constant, x square x term constant. So these are the roots. Okay, so same I am writing. So minus b. What is minus b here? It is the minus b. 2 zeta omega n is the minus b. Plus root of b square. What is b here? 2 zeta omega n. 2 means square. We square it 4 zeta square omega n square minus 4ac. Okay, minus 4. What is 4 here? 4 constant term. So a means constant 1. C also omega n constant. So minus 4 square divided by 2. Take the 2 common here. Here minus 2 there, take 2 common. Automatically 2 will take common 2 to cancel out. So minus zeta omega n plus or minus omega n root of zeta square minus 1 will get here. Right? Therefore, right? So these are the roots of the second order classic equation. These are standard roots. So minus zeta omega n plus or minus omega n root of zeta square minus 1. Okay. So depending on the roots of it may be purely imaginary, called as underdamped. When purely imaginary, underdamped. When it is real and equal to the system, we call it critical damped. When the roots are real and unequal, the system is overdamped. Okay. So by using the roots of the system also can define the what is the type of the system. It may be imaginary, it is undamped or undamped or overdamped. Right? So by using roots you can find the here. Then if you value 0 to 1, the value is 0 to 1, you substitute in this case. So what is the value? You will get minus zeta omega n plus j omega d. What is omega d? Omega n root of 1 minus zeta square is called as a damped frequency. Omega d is called as damped frequency. Okay, you are taking the value 0 to 1 between the 0 to 1 here. Now I am taking the 0 to 1 means that I am taking take the minus 1 in the outside. So 1 minus zeta square. Take down, so we will get automatically j will get here. So here real term, imaginary term, real and imaginary. Okay, so these imaginary term we are taken separately here. So omega d equal to omega n square 1 by ZS, which is called damped frequency. Okay, damped frequency. Omega n is the natural damped oscillations. This one omega d is the damped frequency oscillation, right? So this is the how find the roots of the second order equation and how the system is classified in different types, right? So these are time response second order system by using the unit step. You are using only unit step. I told now you are using the unit step only. You are using the finding the response of the system. Okay, so in this case, I are using only unit step function, not on other ramp, parabolic or maybe impulse. We are using only unit step function. The time response from second order system is the time response here. You can see time response of system under damped using case when input is step input. Right now, this is the standard second order equation. C of s by r of s equal to omega n square s square 2 zeta omega s by omega n square. So I'm taking it between the 0 to 1 the value. Okay, the roots are denominator taking the complex conjugate. Okay, the roots are denominator may be so s equal to zeta omega n plus or minus omega n root of zeta square minus 1. Okay, since zeta is less than zeta square is also less than 1. Okay, so I'm taking the value. So I'm assuming this is the b. So b equal to minus zeta omega n omega root minus 1 omega. So I'm taking already I told previous case. Yeah, I'm taking it. Previous slide I told no. So minus omega. I'm sorry, my omega zeta omega plus or minus j omega root of 1 by zeta square. What is this taking imaginary term we are taking here? So we call it damped frequency oscillations. Now we can represent s with only minus zeta omega plus j omega d. Okay, now I'm finding the response of the system by applying the step input. Okay, now r of s equal to omega n square s square 2 zeta omega s. So actually this r of s bar, I'm taking the r this side r of s input. So I'm multiplying the within output is multiplying the input. So what is r of s in this case? We are taking the 1 by s. So I'm subtracting 1 by s, r of s 1 by s. So omega n square s into s square plus 2 zeta omega s plus omega n square. Now apply the partial fractions. Partial fractions apply. Okay, so a by s bs plus c. So s square is coming, so that's why I'm taking bs. So bs plus c s square 2 zeta omega square omega n square. Okay, now take the partial fractions. When s equal 0, we can find the value of s1 when other remaining terms. Okay, so omega a equal to 1 equal. Now compared with the standard equation with RHS and LHS. Okay, I am taking for finding the value b and c. What we are doing here? So take the same transfer function to here. Then by applying partial fractions constants. Now take the here. Already a is got a equal to 1 because by substituting a equal to 0, you substitute a equal to 0 in this all term. So equal to a value. Okay, so then 1 by s bs plus c s square plus 2 zeta omega square. Okay, by how to find out the b and c. Okay, now compare the LHS and RHS. Okay, so omega n square equal to s square plus 2 zeta omega s plus omega s plus bs plus c. Now what you are doing done here? Then cross multiplication. Okay, by cross multiplication. Understand? Right? So cross multiplication, we are getting this value. Okay, so omega n square. Okay, cross multiplication. So omega n square s square 2 zeta omega s omega square bs plus c equal into cs. Now multiply s square 2 zeta omega s omega n square bs square cs. Okay, so equating the s coefficients here. So you can observe here in LHS there is no s square comes in here. S square comes in. So what is s square coefficients are there? Only coefficients. S square is there. So 1 you take coefficient 1. Then s square comes b are taken. But this side the s square terms 0. So that's why taking 0. So 1 plus b. So b equal to minus 1. Very simple. Right? Then coming to the s terms. S terms 2 zeta omega s 1 s term is there. Then c of s term is there. But the s term in this side LHS 0. Okay. So I'm taking 0 2 zeta omega plus c. Okay. So what is c equal to? 2 zeta omega. So minus 2 zeta omega right here. Okay, so it's simple. Now substituting in this case. Now I'm substituting the same in previous equation. What is the previous equation? This is the previous equation. I'm substituting here. Right? Now substituting. Right? So c equal to minus 2 zeta. There's printing mistake here. So c equal to minus 2 zeta omega, b equal to minus 1. So take the minus common. So that's why equal to minus here. So previous you can observe here. Here it is plus. Now it is minus. Observe. So now substitute value s plus 2 zeta omega 1 by s, then s square 2 zeta omega square. Okay, so adding one more term, adding and subtracting s square omega square. So what are we doing here? Already you know a plus b whole square. What is this value? A square plus b square plus 2ab. Okay, so just you are framing this one, right? You are writing this one a plus 1. All right, so a square b square is there. You tell a square plus b square. What will happen? A square plus whole square minus 2ab come this side, right? So just applying this simple trick here, that's all, right? You are applying the mathematical equations. Okay, so now 2 s into s plus 2 zeta omega n, so s square 2 zeta omega n plus omega. So just you are adding and you can observe adding and subtraction. Nothing are done here. Then what is done here? So s square 2 zeta omega ns. Then I am taking one term in this side. Okay, so zeta square omega n square. I am taking this term this side. So omega okay. Then omega n square I am taking this side. Omega square just omega. So I am just you are shifting the some terms here. That's all. You are shifting the terms. Okay. So s square 2 zeta omega square zeta omega. So what I told now? Okay, a plus b whole square. Right? A square, s square, b square, zeta square omega square 2ab. So 2 into s into zeta omega n. Clear? Then we are I am taking the omega n square common, omega square, so 1 by zeta square. Right? Only by applying the mathematical application I am getting this one. Okay? Right. Then omega d, I am assuming omega d, already you are seen previous slide, omega d equal to omega n square 1 by zeta square. I am taking the omega n zeta square, so 1 by s plus 2 zeta omega, s plus zeta omega whole square, omega d square. Right? Then I am splitting. Here I am splitting. So that from the denominator value I am splitting here. And what is the s plus 2 zeta omega? Two terms are there, 2 zeta omega. So one term I am taking here, one term I am taking here. Okay, s plus zeta omega, zeta omega. Okay, so now 1 by s plus zeta omega whole square plus omega d square, zeta omega s plus omega whole square plus omega. If you take the LCM, you get the same value. If you take LCM here, you will get the same value, right? Then apply dividing the by omega d. So I'm taking the omega d in numerator denominator. Okay, omega d. Okay, in third term, this term I am applying a omega d, dividing and multiplying. Dividing and multiplying means automatically one value. Dividing and multiplying. Okay, so I am taking the zeta omega and I am taking separately. Omega d. So cancel out omega, automatically same value you are getting here. Just I am dividing and multiplying the omega d value. Right? So only for inverse Laplace transform. Right? Now this is the 1 by s plus zeta omega, s plus zeta omega whole square omega d square. So this is called as a e power zeta omega n d into cos omega dt. Right? Coming to here. So I am keeping as this value. So the omega d by s plus zeta omega square omega d. So omega d will sin term. Here we will see this is s plus zeta omega, s plus zeta omega will be cos term. Okay. So e power zeta omega n d into sin term. Sin term and cos term, that's all. Okay, you are applying inverse Laplace. For applying inverse Laplace for inverse easily, that's why just you are splitting and adding some value, adding some omega d and zeta omega, right? Then coming to next, then you can see here, see 1 plus e power I am taking the common, right? Taking the common. So inside cos omega dt plus zeta omega square root of 1 by zeta square, the same here. So I am substituting what is omega d. Okay, in next step I am just substituting what is omega d. So omega d omega square zeta square sin omega d dash I am keeping. I am keeping. Here also I am giving, so taking the this term and this term common. So I am substituting omega d equal to omega 1 by zeta square, right? I'm substituting here. Okay, then 1 minus e power zeta omega nt cos omega dt zeta by 1 by zeta square sine omega dt. Okay, then I am cross multiplying. I am taking again this value common. I am taking this outside. I am taking the common. When you take the common, when root of 1 by zeta term is not there here, so just multiplying it. So zeta sin omega dt, right? So I am taking the outside this value, right? So if there no term root of 1 by zeta multiplied, again if you take the inside, it will cancel out, you get the same value, right? So the mathematical simplification. So the simple mathematical simplification, right? Now to take the triangle, so this theta, this one, this is the root of 1 by. What do you take the theta here? What is sin theta now from here? Sin theta, right? Or cos theta. Sin theta, cos theta, tan theta. Understood? So tan theta means here opposite by side. What is sin theta? Right? Opposite by adjacent. Cos theta adjacent by adjacent. We get like this. Right? See here. You can observe here. Right? So cos omega dt. Cos omega dt. Sin omega dt. Right? I am skipping as it is. So root of 1 minus zeta square. Root of 1 minus zeta square. Sin theta equal to. So sin cos theta. So cos theta equal to will get. Similarly here sin zeta. What is zeta value? From here zeta value. Okay, this is zeta value. So sin means divided by adjacent. Okay, you will get here. So like that you will get the value, right? So they will, by this triangle you are getting the sin theta and cos theta. Now you will get sin A cos B, sin A. So sin A plus B, I am taking sin B. So mathematical in trigonometry, sin A plus B, sorry, sin A plus B. So sin A cos B, cos A sin B. So I am applying here. Okay, so these are trigonometrical simplification I am applying here. So simply you will get the 1 minus e power minus zeta omega t root of 1 minus square sin omega t dt. So this is the second order response when apply the step input to the system. This is very important. So from exam point of view, this derivation is very important. Okay, just to you practice 1 or 2 times in rough paper, then you easily will remember. Okay, so this is the response of the second order system. Okay, so this is the response of this second order system. So peak value, call it a peak value, right? Then it called a rise time. This is called a delay time. Call it a rise time, delay time, right? So this is the final value. The difference between the steady state and the this one called as error. Okay, tolerance, call it tolerance, right? So these are the time domain specifications. Then next is to have to find out the time domain specifications. Okay, so these are the time domain specifications. So delay time, right? Delay time, rise time, right? Then peak time, maximum overshoot, settling time. So these are the time of this second order system, right? Now we'll define each time, that is each time domain specification. So take the first one. What is delay time? So it is time taken for the response to reach the 50% of the final value. 50% of the final value, you can observe here. So 50%. Suppose take the 100%, 50% value. Okay? Time taken to reach the 50% call as a delay time. Then coming to the rise time. So it is time taken for the response to reach the to reach 0 to 100% for the first time, very first time. Because it is for underdamped system. Then it will reach the 90%. You call it critical damp or cold damped system. Okay, 90%. So that is the response of the observe here. So this is the 100%. Sometimes maybe 90%, 100%. Okay, like so this is called as rise time. Okay, right. Then peak time. It is the time taken for the response to reach the peak value. So this is peak value. Time taken. So this is time taken. This is because time axis. So time taken to reach the peak value. Okay, peak value call it peak overshoot, right? Then peak overshoot. Peak overshoot is the peak overshoot, right? Peak overshoot. So it is defined as the ratio of the maximum peak to measured from the peak to peak value, measured to the final value. Okay, it is the defined as the ratio of the maximum peak value measured from the peak value to the final value. Final value, this one final value. So we call it a peak. Okay, this is called as a peak overshoot, right? Then settling time. It is the time taken of the response to reach and stay within the specified limits. Within the specified limits, call it specified error, call it some error. Specified limits, because specified. So within only can be. So we call it a settling time, right? So rise time, delay time, peak time, peak overshoot, then settling time. These are the time specifications of this second order system, right? And you have to find the each value. So what is the rise time, peak time, delay time, maximum settling time for each? Yes, ma'am. Now take the first one, rise time. So see, I am taking the standard second order equation after applying unit step input. So 1 minus c power minus zeta omega t root of 1 minus zeta square. So sin omega dt plus theta. Right? So c of t equal to c of t. I got the equation t equal to r I am taking. So I am taking the 1 value 1. Okay. So this I am equating to 1. Okay, rise time. So because it's under damped system. For under damped system, rise time equal to I'm taking 1. Okay. If you take the 1 here, 0. So I'm taking the same. Then I'm taking from this one to this side. So automatically it will become 0. I'm taking this one this side. Okay, this plus 1 becomes it is minus 1 is equal to 0. Equal to 0 will get it. So minus e power omega zeta tr. I'm taking in place of t tr. So root of 1 minus zeta square sin omega d tr plus theta equal 0. Okay. When sin theta becomes 0 or 1. Okay. When e power zeta not equal to 0, then the term omega d is equal to 0. Okay. When the sin value is 0, when sin value is 0, when sin equal 0, when sin value is 0, sin theta equal 0, when theta equal 0, sin value is 0, when theta equal to pi, it is sin value 0, when theta equal to 2 pi, sin value 0, theta value sin. So like that, the value when the phi equal 0, then sin value is 0, right? So like same condition I'm taking here. So omega dt tr plus theta equal to pi. Okay, so omega d equal to pi minus theta. So tr equal to pi minus theta by omega d. What is omega d? Already you know. Omega n root of 1 minus theta square. Omega d already you know. Okay, so from right angle triangle, tan theta equal to what? Tan theta opposite by side. So opposite by adjacent. Opposite by adjacent. Okay, so I'm taking here from the. So omega d equal to omega root of 1 minus square. So substitute here. Substitute or keep it as it is, no problem. Okay, substitute here, will get the at the end value. So then coming to peak time, to find the peak time, what is the peak value? So that difference with respect to t. When generally in a mathematics you have to find the maximum value or peak value, what you will do? Differentiate the same system and make it 0. So this is the simple in mathematics. Okay, when you are finding the peak value of that system, what will do? Differentiate that with respect to time and make it equal to 0. So the same rule is applied here also. Okay, d by dt c of t and t equal to I'm taking tp and make it 0. Now I'm taking the differentiation second order system with respect to t. I am the respect to t. With respect to the constant value 0. So this is the value. Then sin becomes cos. Sin becomes cos. Then again omega dt is there. Sin becomes cos, right? So then this is the e power zeta omega n t. And g power omega n equal come here. Zeta as it is come. Then again with again e power minus zeta omega get. So in place of sin equal to cos here omega dt. Okay. So this, with respect to t, I am differentiating the respected this one. That's all. Okay. Okay. UV formula d by dt UV formula applying here. E into dv by dt plus v into dv by dt. I'm applying UV formula to here. Okay. Okay. I'm applying UV formula. Right. So differentiate first term, second term for first term, again second other term. Okay. Differentiation only. So by differentiation only get this one. Right. So this is the omega d equal to previous case. So this one, then I'm differentiating, you will get this value. Okay. Right. So by simplification, again I am applying the from the triangle applying the same thing here. Okay, zeta omega n sin omega dt. So zeta omega n, so root of 1 minus omega square e power. So I'm applying the same rule here. Okay. So I'm taking the zeta omega n outside. Zeta omega I'm taking the outside, right? Then zeta omega n outside. Zeta sin omega dt plus t. I'm taking again here. Zeta term here. Okay, cos omega. Okay. So this is cancelled, right? So I'm taking outside. I'm taking common root of 1 minus I'm taking common. So here I'm taking which terms are taking common? E power omega zeta omega and t1 common, then 1 zeta, then 1 by root of 1 minus I'm taking common here. Okay, nothing to here. I'm taking the common here, right? Right. So I'm taking the common. So here I'm applying the from right angle triangle applying the same. So what is zeta? Right? Zeta equal as cos theta. Adjacent by opposite. Adjacent means zeta, hypotenuse 1. So cos theta. Okay. So sin theta, opposite by opposite hypotenuse. Opposite root of 1 minus square. You can observe here. Yeah, you can see here. So opposite by hypotenuse. So sin. Adjacent by hypotenuse. You got cos. Right? The same rule I am applying here. Right? Just simplify the term. So again, what you will get here? You can observe cos, sin, cos. Okay, sin a minus b, because minus there is sin a minus b. Applying same rule here, sin a minus b. So omega n root of 1 by zeta square e power zeta omega n t, right? So sin omega dt plus theta minus theta will cancel out. So automatically get omega n root of 1 minus e power omega sin omega dt. And make it equal to 0. So what is condition? Make it equal to 0. So this all term will become 0, right? So only you'll get here sin omega dt dt, right? Sin omega dt equal 0. I'm taking all the term equal 0. Only sin omega dt equal, I'm substituting t equal to tp now. T equal to, in place of t, I'm typing tp. So sin omega dt equal 0. So when it equals 0, when it is 0, pi, 2 pi, 3 pi, I'm taking only pi. So omega dt pi equal pi. So t equal pi minus omega. So previously also in rise time also same thing, same simplification I have done. Same simplification. There you will get pi minus theta. Okay, here pi by omega d. There pi minus theta by omega d. Here pi by omega d. What is omega d? Omega root of omega n into root of 1 by zeta square. So t p equal, this is the equation. Right? So simple way to find out the peak time. Okay. Then peak overshoot. Okay. Peak overshoot, another peak overshoot. So peak overshoot percentage of peak by peak overshoot minus when you apply the infinity in place of t, then c infinity. Okay. Peak overshoot t equal to tp. Now I am taking the c of t equal to 1 minus e power zeta omega and it's a standard equation. Okay. So when I substitute t equal to infinity, what will happen? This one 1, because t becomes 0. Right? So it is 1. When t equal tp, so in place of t equal pi by omega d, substitute here. So you will get this equation. Substitute in same. So omega d equal omega square, substitute in this equation. Right? So I am substituting here. You can observe c power tp minus c infinity. Okay. Right? C power into. So what c power 1 place this value. You can see sin theta not. Sin theta I am taking minus sin theta equal 1. Okay, so minus. So 1 plus e power, same value applying here. So minus 1, because already you seen the minus 1 is the c when you substitute infinity to the equation becomes 1. So 1 equivalent. Okay, so take this 1 value. So 1 means 1 already. So 1 means here, take the minus 1 cancel out. So 100 into e power minus 2 omega t. So this is the maximum peak overshoot of the equation. Right? Simple. So then derivation of the settling time. So generally settling time you are taking the plus or minus 2 percentage of the overall percentage. So the 100% you are taking plus or minus 2. Okay. So t equal to 0.9. I am taking 100 or 0.1. What is 1 minus 0.2? 0.98. Right? So there I am taking the 2%. When you take the 2%, substitute in main equation t equal to substitute value equal to the 0.02. But 0.2 apply the log, because L and E apply the value. So minus 3.20 is only 4. So t is equal to 4 by zeta omega. Okay, very simple, right? Then apply similarly, same thing apply for next value, plus or minus 3, plus or minus 5%. You get 3 by zeta omega. Okay, very simple here. So ts by 4 by zeta omega, ts by 3 by zeta omega. Okay, for 2% tolerance or 5% tolerance. Okay, 5% 0.95 will get here, 0.95. Okay, substitute in main equation. Okay, main equation, you get this value, right? So this is the way to find out the value. Next, find out the delay time. Generally in delay time, we are taking the delay time is 50% of the system, no? 50% of system. Okay, so c of t equal to, this is the main derivation already, you know. Okay, so 50% of the time response. So this value I am taking 50%, 0.5. This equation as I am taking here. Now take this value this side or this value this side. So we'll get the e power zeta omega dt 1 by zeta square equal to 0.5. Okay, now apply this here. So delay time td. So td equal to, apply here. So 1 plus 0.70 into omega. So this is the delay time of the second order system. Right? Now I am taking the simple one example. So this is the transfer function I am given. Find all the time specifications. Okay, just compare with the standard equation. Keep it in mind very. So denominator is classic equation. So this value. So square plus 2 zeta omega square plus omega n square. Okay, compare with this one. Compare the main equation. Okay, so s square plus 2 zeta omega ns plus omega n square equal to s square plus 10s plus 100. Okay, s term. Then take the 2 zeta omega equal to 10. So 2 zeta omega 10. The omega n square 100. So omega n square 100. So omega equal to 10. 2 zeta omega 10. Find out zeta value. Then when after getting the omega n and zeta value, so you can find out the omega d omega n into root of 1 by zeta square value. Then td equal to delay time 1 plus 0.7 zeta by omega n. Substitute all the values. Then tr equal pi minus theta by omega d. Pi already you know. So this comes in radians. Keep it in mind, after getting this value, this becomes radians, right? Then tr, pi minus theta, Then TS, settling time, I am taking the 2% here. So 4 by zeta n, 4 by zeta omega n, substitute. Okay, just after finding the zeta and omega, remember the, you can keep in, remember the time and specification, just substitute the values omega n and zeta, you will find out the value. So percent pk coefficient you can find out here. Okay, so this is the simple way to find the time specification for a given transfer function. Clear? Thank you so much for patiently listening time specification, time domain analysis. Thank you.